Class we introduced the variational asymptotic method in terms of what the mathematical procedure involves, and also we presented an example involving a quadratic functional, and we saw how that could be minimized. One is the utility of the example per se in terms of understanding the application of the method, but also it will be useful in the specific example that we have in terms of applications, namely to the beam, because even there quadratic functional is involved. And as I pointed out, it would have components which are bilinear as well as linear. The bilinear part coming primarily from warping interacting with itself, warping field interacting with itself, and the other is the warping field interacting with the 1D strain field, which will produce some of the linear function part of the quadratic function. So let's now start applying that to a beam problem. We will apply to a more generic composite beam problem a little later with initial curvatures in all three directions. That's basically the free twist and the two initial curvatures. But to start with, we'll keep things simple, and let's say we have initial curvature in only one direction, and also we will simplify the deformed configuration in such a way that we have a simple situation where we have a symmetric cross-section about a plane, and the loading is also symmetric about it, and the material distribution is such that all the deformations take place within the plane, and the plane that we will choose for that is the plane of the screen that you have over here. Okay, so this is what I was talking about. So the dark portion that you see over here is the initial configuration of the reference curve of the beam. So that's basically written with a small r over here, and it has an initial radius of curvature r. So in other words, your curvature would be given by 1 divided by r, and x1 as usual is the coordinate along the reference curve, and because of the fact that the initial curvature is assumed constant throughout the length, in other words, whereas in general your small k can be a function of x1, in the simple example that we are going to take, small k is not a function of x1, it's a constant, and it's given by 1 by r. Now we introduce a coordinate system A1 and A2. This is the usual A frame that we talk about. Basically a frame motion we know, and basically the beam initial configuration is described with respect to that. So in the picture you only see A1 and A2, so obviously A3 is perpendicular to that, coming out of the board for the right-handed system with the right-hand thumb rule, right? And your B1, B2, the small B1 and B2 initially is different at different locations of x1. It varies with x1 as is obvious with any initial curvature involved. And let's say at this point it coincides with A1, A2, and basically rotates around the beam in the initial configuration. This is the unloaded configuration, so there's no deformation which is involved. Once the deformation comes in, basically you have this gray portion, which is basically the deformed reference curve, which is indicated by the uppercase R, as is our usual standard symbol for that. Once again, you could use either the big BI system or the big T system. So in this case, let's choose the big T system, where T1 is tangential to the deformed configuration, just like your B1 is tangential to the undeformed configuration. And then so you have your T1 and T2, and as I said, in this specific case we are restricting to all deformations being within this plane. It's a planar beam problem that you're basically dealing with. The choice of material, the choice of loading, and basically the choice of the geometry of the cross section is such that we'll assume basically everything is happening in the plane. Again, these are not restrictions which are necessary for the application of VAM, but just because our purpose is only to illustrate here how the VAM is to be applied. So we are taking up a simplistic example so that we can follow through the steps clearly, and then we can go on to a more generic problem. So that's the basic idea. Now we can take advantage of the fact that the initial curvature is the same throughout. So instead of using a parameter like x1 as the arc length, we can use phi, because phi is going to be related to x1 and basically r. So we can utilize that relationship to make some of the equations look simpler. So let me summarize what I just described. So you have an initially curved class R beam. So in other words, the configuration is not having multiple order of magnitude dimensions. So in other words, there's no thin wall involved, for example, or it's not a strip-like configuration. It's an class R configuration, which means that the dimension of the cross section in any direction that you take would be let's say some A, right? So that's basically what we are dealing with. So again, to keep things simple, whereas we could extend it to the class S and T later on. In fact, there would be certain subclasses of class S and T for which what we derive would still be applicable, as we shall see. So, and as I said, we limit ourselves to deformations happening within the plane of this screen. The initial radius of curvature is denoted by R. The cross-sectional symmetry about the plane in which the beam is initially curved. So in other words, whatever the shape of that cross-section is, that if you look ahead of the board and behind the board or the screen, basically it is one and the same. So that is the symmetry which enables this kind of a deformation to be possible, along with, of course, the appropriate combination of loading and material selection or distribution. So the displacement field is symmetric about this plane. The undeformed and deformed state geometries are pretty much the same as what we have been looking at in earlier classes, just that things get a little simpler because of the specific configuration that we have chosen over here. So we'll just specialize whatever we have done in the previous classes. We will rewrite that with these simplifications. So, and of course, the main purpose of this exercise is to illustrate how the variational asymptotic method can be used for this problem. And the idea is to reduce the three-dimensional model that we have to a one-dimensional model. The idea is computational efficiency, at the same time maintaining the level of accuracy which is desired. So we are going to go from an energy which is described in the density form as energy per unit volume to something which is an energy per unit length of the reference curve. So that is the goal. The 1D strain energy depends only on the geometrically exact stretching and bending measures over here. In general, of course, you know there are four 1D strain quantities, gamma 11 bar and the 3 kappa I bars. But in this case, because we are restricting it to planar deformations, the only bending that you have is within the plane. It cannot bend out of the plane. Again, torsion would mean that it is basically not remaining planar. So again, these two are left out. So only extension, which is along the reference curve, and the bending which is within the plane or about the 3 direction, which is basically kappa 3 that we are talking about, are the ones which will contribute eventually to the strain energy per unit length of the beam. Then we specialize again for small strain. This is standard for everything that we do throughout this course, so there's nothing new in that. Then we go to the undeformed state. We'll rush through these things because these are very similar to what we have done before. First of all, you have this orthonormal triad, A1, A2, A3. A1 and A2 are shown in this picture. A3 is not shown because it's perpendicular to this plane of the figure. Now we choose R as, again, you have a choice for R. How do you define the reference curve? We have been stating that we have a freedom in terms of what we can choose, the loci of what in the cross section we can choose as the reference curve. Let us say in this case we choose it as the loci of the area centroids. Rather, so we have to distinguish between mass centroids and area centroids, especially when we get into the dynamics in the last class. We'll do that. But right now, as far as the choice of R is concerned, it's the loci of the area centroids, and that's the dark line that you see in the picture. Next, as I said, instead of x1 we can use phi, and the relationship between them is quite obvious because of the circular geometry involved in the undeformed configuration, R times phi. Then you have the unit vectors b1 and b2, which are functions of x1. They change along the length. So as you see, b1 and b2 over here. And of course, instead of calling it as a function of x1, we can more easily write it as a function of phi, and in turn relate it to these unit vectors a1 and a2 using a simple direction cosine matrix. But it's quite obvious that b3, which is equal to a3, is not a function of x1. Everywhere it remains perpendicular and out of the board over here. Next, the position vector R, once again, wherever you choose the origin from that point to any point on the reference curve is your R of x1. So position vector from any fixed point in A to an arbitrary point on the undeformed reference configuration of the curve. Right. Now the position vector to any arbitrary material point would be that R plus your x2 and x3 along the b2 and b3, with one small difference now that b2 is a function of x1 whereas b3 is not a function of x1. So you just have a simplification from the usual general case that you have. Everything else pretty much remains the same. Of course R is a function of x1. And this is the direction cosine matrix that I talked about, relating the small b system to the small a system using this matrix T. So you can see that b3 is equal to a3, whereas the others, the b1 and b2 are related to a1 and a2 in terms of cosines and sines of phi. Few more words about the undeformed state. Once again, the derivative of the position vector to the reference curve in the undeformed configuration with respect to x1 in the frame A is nothing but b1. That's how the unit vector b1 is defined. Again, no difference from what we have been doing before. Now, as far as the vector of the initial curvature is concerned, it doesn't have the b1 and b2 components. In other words, no initial twist and no curvature out of the plane of the screen. Only component is along b3. So, and its measure number obviously is just 1 by r, where r is the radius, initial radius of curvature that you have. So again, we invoke the usual formula that we have in order to determine the vi primes. The reason we need vi primes is to calculate the covariant basis vector g1, which will be defined as the position vector, the derivative with respect to x1. So there the primes would be invoked because all derivatives are in frame A, and so there we can utilize this fact that vi prime is given by k cross pi and k is given by a very simple expression in terms of the initial radius of curvature. So b1 prime you can see is b3 divided by r, which is what is the value of k crossed with k. So b3 cross b1 would be b2 by r. Similarly, you would have b2 prime as minus b1 by r. Quite direct to see that. And of course b3 prime is 0 because b3 remains the same throughout the length of the undeformed configuration. Right. Now we integrate the position vector of the undeformed beam over the cross section. The reason why we do that, this has nothing to do with the application of WAM or anything that our main goal of this exercise is, but just to show the relationship between the undeformed, deformed configurations and the small u, which is the translations that we talk about from the undeformed configuration to the deformed configuration, any point on this to the corresponding point on this, that is the vector u, right? So we'll try to get a physical meaning of that for this example, but it's something which is much more generally valid under certain conditions, and that condition also we will specify once we reach there. So as of now we have the undeformed state. We'll do the similar thing at the deformed state when we reach there. But for the undeformed state we have this r hat. So all that we'll do is we'll integrate that position vector over the cross section. So at a reference cross section, if we integrate r hat, the first term there is r, which is not a function of the cross-sectional coordinates x2 and x3. So when we integrate with respect to x2 and x3, it just gets multiplied by the cross-sectional area, which is using the same symbol that we used in the previous class. And when we come to the second term, which involves x2, b2 and x3, b3, again b2 and b3 are not functions of x2 and x3, therefore the integration over the cross-sectional coordinates x2 and x3 is only over x alpha. B alpha is taken out of that, right? Now, because of the choice that we made in the previous slide of the reference curve as the loci of the area centroids, obviously this is going to go to 0 because that is the definition of the area centroid. That integral of x alpha dA is equal to 0. So basically this goes to 0 and you have a direct relationship between r and r hat. So it's nothing but r is equal to the integral of r hat over the cross section divided by its area. So basically it's like something like saying the average position of all the material points within the cross section is what r is. So R is the loci of area centroid. So as I said, the second term is equal to 0 there, and therefore this is the expression that we have for R in terms of R hat. So it's nothing but the average position of all the cross-sectional points. And this is true only under the specific case where you have chosen the reference curve R as the loci of the area centroids. In other situations, these could have different meanings. Now let's get on to the deformed configuration, that the gray curve that you see over here with an uppercase R written in red. So green is the undeformed and red is the deformed configuration as before. Now the rigid body displacements and rotations are completely accounted for, first by R itself and the position vectors to that from the same point from which you are getting the position vectors to the undeformed configuration, which point was fixed in the A system, that is the system in which whose motion that we already know. Then of course the rigid body like rotations are determined by how the T system is different from the small b system. Both are of course functions of x1. At a given value of x1, how is the T system different from B system will basically give you the rigid body like rotations that have taken place at that cross section. So that is accounted for as well. So here we are of course dealing with planar deformation, which means that T3 will remain equal to your A3 or B3. So that remains a constant, and it's already known. And the curvature vector for the deformed state, again because we are not allowing for non-planar deformation, there is no component along the B1 and B2 direction, there is only along the B3 direction. Already you had an initial curvature of 1 by R. Now we are adding additional curvature there, which is because of the elastic bending which is basically happening of this curve basically, and that additional curvature that you have is what is indicated by the yellow colored kappa 3 bar over here. So 1 by R plus kappa 3 bar is basically your K3 measure that you're talking about. In this case it is K3 because remember that big K always has to be in the big T system, or if we are talking about the big B system. But in this case, the big, small, in the 3 direction alone, you have this correspondence. So in reality, this should have been T3 in a general case. Because of this simplification that we're talking about, only about planar deformation for this pedagogic example, therefore, T3 gets replaced by small b3 utilizing this particular equation. Otherwise, these two would have been in the small b system and this would have been in the big B system. This we have discussed in the vector dyadic definition for the elastic curvatures and or the total curvature earlier on. Continuing with the example, Wi are the displacements of points with respect to the deformed reference cross-sectional plane, what we call as warping of course. So they include of course W1, which is the out of plane warping, W2 and W3 which are the in-plane warping of the material points which make up the reference cross-sectional plane of the undeformed beam. Now Wi is of course not known a priori, in fact that is the main unknown that we are trying to determine, whereas the gamma 11 bar and the kappa 3 bar which are the other two unknowns here are functions only of x1. Your Wi is not only a function of x1 but it's a function of x2 and x3, and the application of WAM will make it evident that we can solve for Wi explicitly in terms of x2 and x3, whereas its dependence on x1 would still remain, but it would be not independent but through your kappa 3 bar and the gamma 11 bar which is yet to be introduced in the discussion over here. So Wi is not known a priori, and it's calculated subject of course, one is the minimization of the total potential which is involved, but in addition you also have to take into account the constraints because of the redundancy we have introduced. Instead of 3 variables, 7 variables, and therefore the 4 constraints that we already introduced in the previous classes. So those constraints would enable us to remove the redundant degrees of freedom. Again, I need to stress the fact that those constraints are not sacrosanct, but the way we introduce them gave certain specific meanings to the variables which were involved, and you would see that invoking the same set of constraints that we used in the previous class would also enable a certain physical interpretation of the deformed configuration variables in this example as well. So the position vector for the same material point in the deformed beam to which r hat points in the undeformed beam is what we want to determine now. So you're tracking one particular material point. You already have a reference curve. On the reference curve, you're choosing a reference cross section. On the reference cross section, you're choosing a particular material point and tracking it down, what happens to it as it translates and rotates and warps, what basically happens to that particular material point, which is a function of x1, x2 and x3. So that's basically what you're tracking. Obviously that should depend on the rigid body translations, the rigid body rotations and the warping variables, all of which are involved. And that position vector, as in previous examples, is given by r hat is equal to, first track down the reference curve and the reference cross section on which it belongs. Then you know where it has gone because of the rigid body translations, and then because of the rotations which are involved, you have x2 t2 plus x3 t3. But once again we invoke the fact that t3 is equal to b3, so we can substitute t3 as b3 over here. So that's the only difference from what we have been doing earlier on. And of course you have the wi components along the big Ti as usual. Now let's do a similar thing what we did in the previous case for the undeformed configuration. With the deformed configuration, what we did there was, once we got this expression, we integrated this equation over the cross section and showed that the small r is nothing but the average of the big R hat over the cross section. So let's see if you have a similar kind of a situation over here as well. So integrate over the cross section. Once again, the symbol that we use for that are the angular brackets. And once again, big R is a function only of x1 because it tracks just points on the reference curve, and therefore you just have R multiplied by the area when you integrate over the cross section. Once again, t2, b3, etc. are all either constants or functions only of x1, and therefore they come out of the integral. And you end up with, once again, integrals of x2 and x3 and integral of wi. Once again, invoking the same kind of constraints that we introduced last time, that is average of wi equal to 0, which is basically the first three constraints which removed the so-called rigid body translations. So that way of introducing the constraints would enable a very interesting description of R in terms of R hat, just similar to what we had for the small r and small r hat previously. So once again, the second and third terms, because of the choice of the reference curve as the loci of the area centroids, these go to 0. And the choice of the constraint, warping constraint, this goes to 0 as well. And you have an exact analogy that you had in the undeformed configuration in the deformed configuration as well. So that is R is equal to the average of R hat. So a similar interpretation literally means that the big R is nothing but the average position in the deformed state of those points which are making up the undeformed beam cross-sectional plane. So the same set of material points you are just tracking, which were on the reference cross-section, and you know where they have reached now, and then you average out their positions. Whatever average that you get is nothing but your big R according to this equation. Next we go to the small u, which is basically the displacement vector, a one-dimensional variable in the sense that it's spatially function only of x1. So what is that? So because that is going to be related to your big R and small r as if are their difference basically, and that is what is u. So now that we have an interpretation for big R and small r, we can get the physical interpretation for small u as well for this specific choice of constraints and the specific choice of the loci of the area centroids as the reference curve. So u is nothing but the vector from point on small r to the corresponding point that is the same x1 of big R. So which means that big R is nothing but small r plus u. Now we will utilize the equation that we derived for like this for the undeformed configuration as well as the deformed configuration, and then basically see what it means. So you take u to the left hand side, bring the big R hat and small r hat to the right hand side, and this is what it ensues, which basically means that now you know that big R hat minus small r hat is just basically the translation of each and every material point from the undeformed configuration to the deformed configuration. You are integrating that over the entire cross section. Dividing by the cross sectional area means that it is the average translation of all the material points. So that is basically the average displacement of all points contained in the undeformed beam reference cross section. So it's a very clear physical meaning for that under the special condition in terms of the choice of constraints and choice of the reference curve. Wi is measured with respect to translated and rotated planar image of the undeformed beam cross-section plane, and of course U is not the displacement of a specific material point in 3D structure. So U has a meaning of some kind of an averaging out of what is happening with respect to all material points. It's not necessarily the translation of a particular material point. Let's say you are trying to track a point which coincides with the intersection of the reference curve with the reference cross section. It's not the translation of that point that basically is U. So that's an important thing to remember. That material point might have moved elsewhere. It may not be the same material point that is still on the reference curve. That's what U basically does. It just averages out the motions of all the points on the cross section. So that's something to be kept in mind for this choice that you have made in terms of the configuration and the entities involved with the modeling. Now we specify the rotation based on the type of theory to be derived. That is either we're talking about the small local rotation theory or the medium moderate local rotation theory, etc. Here we are focusing, of course, on the class R beam and a very simplistic example of only planar deformation. The first thing we do is derive classical theory, and in fact that would be the case even when you're considering a more complex example, complicated or general example. Even in such a situation, the first or so-called zeroth order approximation to the RAM would indeed be the so-called classical theory, which does not account for the transverse shear deformations because they are higher order effects for all beams. Okay, so neglects the transverse shear deformations. The cross-sectional plane of the deformed beam is perpendicular to the tangent of R. So in other words, the reference curve remains perpendicular to the reference cross section as far as this is concerned, right? So what does that mean? So basically, in other words, your T2 and T3, which are in the cross sectional plane, will be perpendicular to the tangent. The tangent is nothing but the derivative of the position vector with respect to the arc length in the deformed configuration. So in this case, it's basically dr by ds, rather than in the small r case, it was dr by dx1. So which we could have just written as a small r prime. But here it is not so, it is dr by ds. But once again, the derivative is taken in the frame, in the same frame A in which all references are made, right? So which in turn, because of the fact that we are talking about a triad T1, T2, T3, where T1 is perpendicular to both T2 and T3, therefore if the dot product of T2 and T3 with this vector is 0, then it means that this vector is parallel to T1, right? Because T1 is perpendicular to the plane of T2 and T3, right? So in other words, dr by ds in the frame A is basically parallel to the vector T1, the unit vector T1, right? So that is as far as the direction is concerned. Now we need to get the magnitude, right? So now S is nothing but the running arc length along R, which means that dr by ds has to be a unit vector, okay, always. That is something which you can prove using basic geometry, right? So dr by ds is nothing but the unit vector because S is the arc length, which we already know the direction, and we also know its magnitude because it's a unit vector, and we know the magnitude of this is also 1. So basically dr by ds is equal to some constant into T1 is what this says, and that constant is equal to 1 is what this says, and therefore a dr by ds is nothing but your big T1. Right, now define the local stretching strain measures in this case as just gamma 11 bar is equal to S prime minus 1. So in the case where there is no change in length of the reference curve, your S and X1 will coincide, and ds by dx1 would be nothing but 1. So it will be 1 minus 1 equal to 0, no change in length. When S prime is, S is such that extension is taking place, your S prime will be larger than 1, and you see that you will have a positive extensional strain of the reference curve. Similarly, the contraction is taken into account as well. So your gamma 11 bar is equal to S prime minus 1. this would not have been the case if we had not neglected the transverse shear deformation, or in this situation when we go to higher orders approximation, when that transverse shear would automatically be captured by using the variation asymptotic method, you would see that this is not an exact relationship. Gamma 1 to a bar, or rather there will be no bars there, gamma 1 2 and gamma 1 3 would also contribute to a change in S in some way, but in a smaller way compared to gamma 1 1 bar. But this is the leading contribution to that. So we can just put the 1 on the other side, and therefore you can get an expression for S prime as 1 plus gamma 1 1 bar, because eventually we want to express this in a particular way. So S prime is equal to 1 plus gamma 1 1 bar. Now we will need R prime, because we are later on going to determine the 3D strains for which we need the deformation gradient tensors, which in turn means that we need the covariant basis vectors in the deformed configuration, for which we have to take the derivatives of R hat with respect to x1, and that will also involve a derivative of big R with respect to x1. So we need to know what is big R prime. So let's take big R prime. That is nothing but, by definition, it's nothing but derivative with respect to x1. All primes are derivatives with respect to x1. And if the derivative that we are taking off is of a vector, then obviously the frame is specified to be A. That's understood by the way we have defined this particular notation. Okay, that prime means derivative with respect to x1 in the frame A. Because for a scalar it doesn't matter, the frame doesn't matter, but if it's a vector or a dyadic, then the frame is important over there. Now we can use the chain rule, invoke the chain rule. So derivative with respect to x1 can be written as a derivative with respect to s, and the derivative of s with respect to x1. This is nothing but s prime, and for which we have already obtained an expression over here. We can go back, substitute that over here. So T1, and this is of course T1 as we already showed over here. So we take both of those into account, and therefore we can write R prime in terms of one of the 1D generalized strain measures. Now you know that if you had taken the big B1 system and you had accounted for the transverse shear deformations as well, this would have instead been 1 plus gamma 1 1 along big B1 plus 2 gamma 1 2 along big B2 and plus 2 gamma 1 3 along big B3. Okay. So it's just that we are using the big T system, and also right now we are focusing on the classical theory, the zeroth order approximation. So those terms are basically not contributing. The other way to look at it is we are using the big T system, and that is in some way included in the warping, and therefore we will not observe its effect over here. To complete the rotation specifications, you need of course another rotation, which is to define the rotation which is taking place about T1. And that has to be accounted for by the fourth constraint. So remember, we already invoked the three constraints, that is Wi average equal to 0 when we defined, let's say, u for example. But we have not yet talked about the rotation constraint, which is x2w3 minus x3w2 integrated over the cross section equal to 0. So that helps us to define the rotation of the deformed cross-sectional plane about the T1 axis. And choose this rotation to satisfy the fourth warping constraint. That's what I just mentioned. So the constraint choice, again, as I mentioned, is not sacrosanct, it's not unique. It should render a unique displacement field, however. Okay, so that is the whole idea. The reason why we are introducing the constraints is to remove the redundancy that we ourselves incorporated in the model by introducing more variables than are necessary, 7 instead of basically 3. So we needed the 4 constraints. So how we choose those 4 constraints, there's a lot of freedom, but it's not unlimited freedom, because it also has to ensure that the displacement field which follows out of it is indeed unique. So you cannot have constraints which still have some redundancy involved in there, or in other words, for example, constraints which are linearly dependent on each other, for example, would be a case where you would have not entirely removed all the 4 orders of redundancy that are involved. So your entire displacement field, the displacement field, should be rendered unique by the choice of constraints, and this is the 4th constraint, which is one of those such choices which enables the redundancy to be entirely removed. Now the strain is defined based on the small local rotation theory. Remember that we are restricting ourselves here to the class R beam, but as I said, there can be some specific loading cases in class T and S beams for which also this might be still applicable. But let's look at this. So there, again, even though we invoke the small local rotation theory, again, as we said, it is something which is a fallout of the small strain itself. Because of the small strain, therefore, the local rotations are small for such cross sections. And despite that, there are no restrictions on the size of the reference line's displacement, that is the rigid body-like translations, or the cross sections rotations, which are the rigid body-like rotations of each cross section. Those can continue to be large. It's only the warping which is small, so that the strain is small, and therefore because the warping is small, its derivatives with respect to x2, x3 in particular, and of course with respect to x1 are all small, and therefore contribute to small local rotations within the cross section, different from other elements of the cross section, same cross section. What this means is that it's valid for large deflection analysis of isotropic class R beams. Of course, there are some situations where it can be applicable to composites as well. But again, this is a pedagogic example, and in fact, when we go to the 3D constitutive law, we will take isotropic constitutive law so that we can basically see the actual terms in the strain energy, what they are, which are the leading terms, etc. It becomes much easier to illustrate that in a class. But in the next class, we will see how we generalize that to the situation where it's a composite, and the constitutive law in the 3D is much more complex than what we will deal with today. So it's suitable even for, as I said, not only class R beams but class T beams. For example, if your only stretching and bending is involved and they are made out of purely isotropic materials, not of composites. So in such situations, you can show that even whatever we are going to do today is valid for class T beams as well. Because in such situations you would see that Wi remains order epsilon hat A, okay, and not bigger than that. The situation becomes a problem only when you have local rotations which are larger, which are of course balanced by some other large terms present in the expressions for the 3D strain, so that the 3D strain itself remains small, but two terms are large in such a way that one is positive, the other is negative in magnitude, and therefore basically you see that the difference is what contributes to the 3D strain, and therefore it is small. That's what typically happens with class T beams, but only in situations where there is torsion, because both the class T beams as well as class S beams for that matter are very soft in torsion, and that's where the rotations are much larger, and the corresponding local rotations are large as well, or rather larger compared to the usual thing, what we call as moderate local rotation theory instead of small local rotation theory. Next, the matrix of strain measures in the local Cartesian frame is expressed in terms of the matrix of the deformation gradient tensor measure numbers in the mixed frame, of course. And that is basically this. This is what we have derived for the small local rotation theory, where only the symmetric part of the deformation gradient matrix in mixed form contributes, the local rotations don't, which are basically directly related to the skew symmetric or anti-symmetric portion of the deformation gradient matrix. So now once again we invoke that. These are things that we have seen in the previous example, so I'll go a little faster for lack of time on this. So you have, of course, this is the deformation gradient tensor. You're expanding out in the big B and the small b bases. In this case, maybe the big T could be utilized, and base vectors are needed, defined as before. So once again, your small gi are given as the derivative of r hat with respect to the xi in frame A. From that we get the contravariant basis vectors as perpendicular to the surfaces formed by the pairs of covariant base vectors, and correspondingly we get the metric tensor and its determinant. So the determinant of the undeformed geometric metric tensor, because that is going to be useful as well in more ways than one, as we shall shortly see, because when you are talking about volume integrals, what really happens in a curvilinear system is something most people are not familiar with. So I'll introduce that aspect sometime later in today's class. And that's as far as the undeformed configuration is concerned. You need the contravariant base vectors, but in the deformed configuration you need only the covariant base vectors, which is basically this, and that again is formed very similar to in the undeformed configuration. Instead of taking the derivative of small r hat, we have to take the derivative of big R hat with respect to the xi's to get all three of the covariant base vectors there. So this is the general expression that we have there, and so let's recollect. Your small r hat is given by that. So your G1 is dou r hat by dou x1, which is directly just 1 minus x2 by r times b1, as you can very easily see over there. Of course, the first term b1 comes from the derivative of this, and the other basically comes from the fact that b2 varies with x1 because of the initial curvature that you have, and that's where this minus 1 by r times x2 basically crops up. So that is your G1. Your G2 is much more direct, because the only term in which x2 figures here is here, and the derivative with respect to x2 would just be b2 alone. Similarly, your G3 is just b3 coming from this term. Okay? And then from these three you can get the determinant of the metric tensor and then its square root, and that is nothing but 1 minus x2 divided by r. Okay, so if you had curvature in the other direction, x3 divided by r in the other direction with the appropriate sign would have contributed as well, but that is not to be. We are talking about initial curvature in only one direction, and therefore this is all that is root g. Now we come to the contravariant base vectors. All that you have to do is to take cross products. For example, to get G1 you have to take the cross product of these two, B2 cross G2 cross G3 divided by root G. We have expressions for all of them. All that we need to do is go ahead and substitute that. So B2 cross B3 is B1 divided by 1 minus x2 by r, which is root G over there. Then G2 is similarly found to be nothing but B2, and big G, small g, superscript 3 is also B3. That's again quite direct to see, because the 1 minus x2 by r here will cancel with this 1 minus x2 by r, and you would see that these two reduce to just B2 and B3 alone. Next, so now we have already got this quantity over here. Next effort is to get this quantity over here, the covariant base vectors of the deformed configuration, for which we need the position vector of our arbitrary material point in the deformed configuration. So this is what it is. The only simplification, of course, is T3 is written as B3, but maybe because we want to take the dot product, it's not even necessary. We can still keep it as T3 so that this dot product becomes easier, but they are the same nonetheless. So G1 is nothing but your r hat prime, which is nothing but given by this expression, which is quite easy to see once again. You have to only look at terms which are dependent on x1 over here. Remember that we already talked about the big T primes as well in terms of the initial radius of curvature r and the kappa 3 bar, that expression we had in one of the earlier slides. So we are basically utilizing that in determining T2 prime. Of course, T3 prime is equal to 0 because T3 is equal to small b3 and doesn't vary along x1. So that will be left out. So only T2 prime will basically contribute over there. This term in fact doesn't contribute to this expression at all. And coming to here, both Wi and Ti depend on x1. And here we are taking derivative with respect to x1. So we will have the W primes along the corresponding T1. So W1 prime along T1, W2 prime along T2, W3 prime along T3. And in turn again you will have T1 prime and T2 prime contributing. T3 prime would be 0. So T1 prime would basically contribute a term like this, and T2 prime would contribute a term like this. And so that gives the entire expression. Next is derivative with respect to x2, which is much simpler. A term would come from here, and again from here you would have a dependence on x2. So it's quite clear that this is what you have over here. So each one of the wi's with respect to 2, you have w1, 2, w2, 2, and w3, 2. This t2, of course, as I said, comes from this term over here. The g3 is very similar to that. So you see that instead of a 1 plus w2, 2, you have a 1 plus w3, 3 here. The rest are all derivatives of the warping measure numbers with respect to x3 direction. So now let's go ahead and get this is the summary of what we determined in the previous slide for the covariant base vectors of the deformed configuration and the contravariant base vectors of the undeformed configuration. We just have to put them together to get the chi's, which is basically this. So for example, if you want to determine, let's say j is equal to 1, only b1 would be, small b1 would be involved, and amongst all these, b1 is there only in this. So which means that it will only involve from the g's, the first quantities over there. So for example, your chi11 would directly be taken from this, and of course divided by 1 minus x2 by r. So similarly, it's quite easy to see that your next thing would basically be this term divided by this, and the third thing would be this divided by this. Next, if you want to look at the when j is equal to 2, basically it's only b2 which is terms which are going to contribute. b2 is not there in this, b2 is not there in this. So it's only from this that we are going to have. So it's basically these three terms which are going to be there. And in fact, there's only unity over here. So these terms will be directly appearing in those three contributions. So it's basically w1 comma 2. Next will be 1 plus w2 comma 2. And next would be w3 comma 2. So that's your AE3 2. And finally, you want to get for j is equal to 3. So that involves only b3. And b3 is not there in the first two, it's there only over here. So basically you have to take terms from over here, very similar to the previous case. So this is what you have as expressions for all of the chi's, right? Once you have the chi's, because we are talking about a small local rotation theory over here, because class R beams isotropic is what we are dealing with here. So only the symmetric portion of this chi matrix is useful for us. We have 9 independent components over here, but we will be basically taking the symmetric portion of that, so only 6 quantities of interest would be there. And of course you have to subtract the identity or Kronecker delta over there to get the 3D strains, which are the Jaumann-Biofashi strains, the leading terms. So strain in the local Cartesian system parallel to the BI. Remember that when we expanded out all the relationships and converted them from the dyadic form to the matrix form, we used expansions of all the vectorial and dyadic quantities, and there we expanded the capital gamma tensor in terms of the small b system. So it's basically a Lagrangian kind of a strain that we're talking about here. Not an Eulerian kind of strain, in other words. So basically these are the 6 strain components of interest to us. The diagonal terms are of course the normal strains, and the off diagonal terms are the shear strains that are involved. Now it's very interesting to see that these 3 strains are dependent only on the W's, they're dependent only on the warping. So if in a particular problem or in a particular model you're completely ignoring warping, for example, it basically means that these are 0. In fact, we considered an example, a very simplified example much earlier, where we did that, where we said that the cross section is basically rigid, and basically, in other words, there is no in-plane warping, only out-of-plane warping is there, and therefore all of these terms are equal to 0. But this is a little more general case than that, and we are indeed considering these quantities. And these big R's, of course, are the initial radius of curvature, so terms contributed from that. So if they were not there, for example, these equations would have been much simpler and things that are much more intuitive to you. For example, here the denominator would have been just unity, this term would have vanished, so you would have had only these 3 terms. You know, the extension of the reference curve contributes to the extensional strain, the curvature also contributes to the extensional strain depending upon how far it is from the neutral axis, right? So, and then of course the warping, but this is a very small contribution, W1 in itself is small, and then you're taking derivative with respect to x1, which is along the length, which is the largest dimension in the entire structure. So you can see that those are the 2 leading terms. Similarly, you can see the others are quite intuitive as well. Next, for all beam classes, your gamma 11 is of the order of epsilon hat. That's something which we have taken for all the strain measures, in fact. We are considering a term gamma 11 amongst all the gamma ij's right now. Out of the 6 terms, gamma 11 should also be of the order of epsilon hat at the most, right? It could be smaller than that in some specific examples, but it cannot exceed that. That's what this particular expression, mathematical expression means, okay? So now what that in turn means is that your gamma 11 bar should be of the order of epsilon hat, because if this were bigger than epsilon hat, then your gamma 11 would be bigger than epsilon hat. One of the strain components would be bigger than epsilon hat, or in other words, you would have reached failure of the material. So that is quite obvious. Next, coming to this term that you have here, x2 times kappa 3 bar as a product should be of the order of epsilon hat. So from that we can detect the order of kappa 3 bar. We are considering class R beams. So both x2 and x3 are of the order of A. So in other words, your kappa 3 bar would be epsilon hat divided by A.
Sir,
yeah.
Why can't I have, like, before you said those 2 terms, gamma 11 bar and x2 kappa 3 are of opposite signs. Why can't they be of a higher order and then cancel out?
See, these are two things which are incited by orthogonal quantities. See, these are extracted as degrees of freedom. Okay, so your gamma 1 bar, kappa 1 bar, kappa 2 bar, and kappa 3 bar are independent of each other. In other words, in a real physical case, you can think of the extension is incited by an axial force and the bending is incited by a curvature. So basically a moment, right? So the moment load and the axial load could be independently applied in different orders of magnitude. Okay, so it is not possible that one can compensate for the other. On the other hand, the warpings and therefore the local rotations are all functions of these gamma 1 bar, kappa 2 bar, and kappa 3 bar. So it is possible that the local rotation can act as a combination with one of those. So typically it is the kappa 1 which will act as a combination with one of the local rotations to show that when kappa 1 is large, then therefore your that corresponding local rotation can also be large, such that their sum would still be small, contributing to the corresponding strain measure, should be a shear strain measure. Right? Okay, class R beams, as I said, both the directions, their dimension is of the order of A, so which means that the area would be of the order of A squared. For example, if it's a circle of radius A, or for that matter diameter A, it would just become pi into A squared by 4. So pi by 4 would be of the order of unity, so you can see that it's A squared. If it's a square cross section also, it would be A squared, and so on and so forth. Okay. Of course, it takes into account rectangular and all other cross sections, basically where you cannot determine a small parameter within the cross-sectional dimension. So that's basically the specific case that we're dealing with. And of course, just like gamma 1, all the other gammas are also of the order of epsilon hat. In specific, let's talk about 2, 2, 3, 3 and 2, 3 terms, which are the simpler terms which depend only on the in-plane warping that we already saw over here. Now we know they're all of order epsilon hat. For example, if this is of order epsilon hat, then W2 becomes epsilon hat times A. Similarly, W3 becomes epsilon hat times A, and that doesn't conflict with this expression either. Okay, so here we are taking this W2 which was derived with respect to 2, instead derived with respect to 3, but whether it is derived with respect to 2 or 3, it's divided by A to get the order of magnitude. So this would still be order of epsilon hat if the W2 and W3 were of the order of epsilon hat times A. So that's basically the conclusion that we draw over here. And gamma 1 alpha, now we already saw this, so from this term we got the order of magnitude of these two quantities. From these we got the order of magnitude of W2 and W3. Now we will take up these to determine the order of magnitude of W1. We are not taking this because if we take this as order of epsilon hat, what would happen is W1 would become epsilon hat times L, and when we go here, it would become epsilon hat times L divided by A. And L divided by A is a large quantity compared to unity, and therefore this term would contribute something bigger than epsilon hat, and therefore cause the failure of the material. So we cannot do that. So instead of looking at that term, we're basically looking at these two terms to get the order of magnitude of W1, very similar to what we did with W2 and W3. So the out of plane warping also turns out to be order epsilon hat times A. So in other words, we can combine all of these. W alpha is of epsilon hat A and W1 is of order epsilon hat A. So we can just write Wi is of the order of epsilon hat A, which is the case for class R beams. Next situation is the small local rotation, that is of the order of epsilon hat. In fact, this we already discussed in the general situation where we compared the orders of magnitude of the local rotation with the strain, and we took two cases there, if you remember. One is of the order of epsilon hat, the other is of the order of epsilon hat power half, as the two situations, extreme situations where we had small and moderate local rotation. So in this case, it is class R beams, we have small local rotation and Pi is of the order of epsilon hat. Basically, it's nothing but these are the terms which contribute to the local rotations, and you can see quite clearly that they are indeed of the order of epsilon hat. So there's no assumption involved, it's a fallout of the fact that we are dealing only with small strains. Next, here there is a slight dicey thing over here in terms of how do you handle the initial curvature. So initial curvature is in terms of the initial radius of curvature big R over here, we have more than one geometric parameters to deal with. So we take this situation where this big R and the L are of the same order of magnitude. So which is indeed the case if you looked at the undeformed configuration that you had a quarter circle, or for that matter even if you have a full circle, you know that the circumference of a circle is 2 pi r. Okay, so 2 pi is about 6. So that is not an order of magnitude difference between L, the length of the beam, and the radius of curvature which is involved. So that's basically what we are saying, that R and L are of the same orders of magnitude. If they were different, of course, you would have to take that into account and appropriately derive the theory according to the difference which is basically involved. Both of these quantities are things that you know a priori, the length of the beam and the radius of curvature which is involved. A situation would be very different from this. For example, if you had a beam which was bending around itself, a typical example that I've been talking about in many situations, in which case the initial radius of curvature would be of the same order of magnitude as the cross-sectional dimension rather than of the length. So for that you would have to have a different kind of a theory taking that relationship between L and R into account. And so what we have taken is, of course, a squared by r squared is very small compared to 1. It's not that we are taking just a small compared to r. So in the sense that we are dealing with beams which could be typically such that the cross-sectional dimension is just 1/10 of the length as well, not necessarily 1/100th of the length. Okay, so whereas your strains epsilon hats, because of most materials that we use typically having failure strains of the order of 1% or so, this would be of 10 power minus 2. Your A by R would be 10 power minus 1. So in other words, when you're talking about something small, we're talking in a consistent way. So it's not that we are ignoring A by R terms, we will be ignoring A squared by R squared terms. So in other words, we will have to account for A by R terms as well, which are just 1/10. If we are not going beyond epsilon hat in this, which basically means we are limiting up to 10 power minus 2 over there. So in this situation also we are talking about 10 power minus 1 whole squared, which is 10 power minus 2. So that's the kind of terms up to which we intend to go over here. Next, the strain is rewritten with non-underlined terms and underlined terms over here. So in other words, the same expressions that we had here, but rearranged in a particular way and dropping off of certain terms. And also here you have a 1 divided by 1 minus x2 by r. Here x2 is small compared to r, so we can express this as, let's say, instead of divided by into 1 plus x2 by r and an x2 by r squared term, etc. in a Taylor series, for example. And so from that, then we can drop off terms which are of the order of a squared by r squared compared to the leading terms. So keeping that, what I write here is higher order terms. So we have, let's say, 3 sets of terms. One is the leading terms, which I'm not underlining over here in each of the expressions. And then the next higher order terms, which are a by r compared to the leading terms, that is underlined. And then I'm dropping off terms which are a squared by r squared, etc. So that's basically the so-called higher order terms over here. So basically it's the same set of equations, but written in a way that you are basically segregating and keeping the leading order terms and then the next higher order terms and so on and so forth over here. Similarly, you have for 2 gamma 1 2, 2 gamma 1 3, and these of course remain the same. The expressions are as they are over here. They are of the order of epsilon at a, the warping, and the derivative with respect to x2 and x3 is such that divided by a. So all of these terms are important and they are all of the order of epsilon hat, right? So next, there is something that more that goes into the utility of this root g, the metric determinant that we have been talking about, and that's something we will discuss here, because next we are going to apply the variational asymptotic method, for which we need the functional whose stationary points we need to determine, and the functional will involve an integral over the volume. And the volume that we are talking about here is not a rectilinear volume, but a curved volume that we are basically dealing with, because we have an initial curvature which is involved in the beam. So therefore, what is the volume element in the case of a curved beam is what we want to explore. Before that, something which is directly obvious to us, if we had an initially straight beam, for example, in that situation all three xi coordinate curves would be straight lines, right, along x1, x2 and x3, which means that if you take a volume element along x1, x2 and x3, it would be something like this, which would be a cuboid, right? In general, dx1, dx2, dx3 are different in length compared to each other, but they're all infinitesimal lengths. But the volume element is like this, and therefore the volume element dV, the value of magnitude of the volume, can easily be written by just a product of these three quantities, right? So in other words, your dV will be given by dx3 times dx2 times dx1. On the other hand, let's go to the case we have on hand, because we have an initially curved beam, even though it is curved only in the plane of the board. Let us take a more general example, at least for this slide alone, and we'll deal with a beam which is having all kinds of initial curvature. That is, it has small k1, small k2 and small k3, all three of them in general not equal to 0, right? And so basically your x2 and x3 are cross-sectional coordinates, which are still rectilinear coordinates. So only x1, which basically has to go around like this because of the initial curvatures. So your x1 coordinate is curvilinear, and so therefore your volume element would basically look like this, right? So if you take a small infinitesimal length dx1, there is an initial curvature which is basically associated with that element. On the cross section, of course, you have dx2 and dx3 as before, but for determining the area, for example. But as far as the volume is concerned, you can no longer call the volume of this as dx1 times dx2 times dx3, okay? So it is something different from that. What is it is what we want to determine here. So the volume element is, first of all, non-cuboid, unlike in the previous case. So what is this volume element? So then we introduce this concept of, from geometry with curvilinear spaces which is involved. In such a curvilinear space coordinate system, we go to the basic definition of the volume element in terms of product, which you are very familiar with, a volume product which is involved, where you have a dot product and a cross product between the three vectors which are the base vectors for that system, in particular the covariant basis vectors of the system. So you have G1, G2 and G3. Along G1, G2, G3 you have magnitudes dx1, dx2 and dx3, multiplying them. And of course this can be written in a cyclic manner in different way. You can put dx2, G2 over here and then put the three quantity here and the one quantity here. Doesn't matter, but basically this is the way the volume element has to be calculated, and of course the magnitude of that, because the volume is positive, right? So of course dx1, dx2 and dx3 are basically lengths. They are positive and they are scalar quantities, so they can be taken out of this entire thing. So basically you have dx1, dx2, dx3 out, and then the magnitude of g1 dotted with within brackets G2 cross G3. So this is basically what it is. Now we can utilize the fact that the contravariant base vectors, which we have already determined, are given in terms of these cross product. For example, we know that G superscript 1 is G2 cross G3 divided by root G, right? So we can write this as root G times that contravariant base vector. So we can write G2 cross G3 as basically this. G superscript 1 into root G. Now you have a very familiar thing over here, G1 dotted with G1, where the first one is a covariant base vector, this is a contravariant base vector, and as a pair they behave like orthonormal systems. So basically this is nothing but the Kronecker delta function delta 1 1, which is equal to unity 1. So that's 1, and therefore you just have the magnitude of root G, which is this. So square root of G times dx3 dx2 into dx1. So this is what is the volume element in the case of a curvilinear coordinate system. So unlike here where we just could take dx3 dx2 dx1, here we have to take root G into account as well. Of course this is a more general definition which can be specialized for this, because in this case root G is equal to unity, right? So the expression for root G, not for the specific example that we are considering in today's class, but a more generic example where you had not only K3 but also K2 non-zero values, is basically this. And again, even if K1 is equal to not equal to 0, that is you had pre-twist, that would not contribute to root G, okay? So and even if K1, K2, K3 all varied along the length, this is something which would still be valid, okay? So this is what you have for the expression over here, dx3, dx2, dx1. And for the special case that we have here, k2 is equal to 0, k3 is equal to 1 by r, and that is something that we will take further for this example. So the volume integral of any quantity if you want to take, so this is of course a volume element. Now if you want to take the volume integral of some other quantity, let us say we represent it by this star, then it can be broken up into two parts. One is the integration over the cross section, the integration over the length. But in either case, you would have not only dx3, dx2, dx1, but basically a root g as well, which is whose expression is written from what we had over there, right? And of course, because it involves, this expression involves x2 and x3, that cannot be brought out of this inner integral you have over the cross section. There is a dependence on x2 and dependence on x3. So therefore, you see that it has to be within the inner integral as well. Okay, of course, k2 and k3 will be functions of x1, and therefore integration over the length will take care of that aspect as well. But the danger is you cannot take this term out of this square bracket. That's what I'm saying. So therefore, in our specific example, dV is now 1 minus x2 divided by r multiplied by the three elements dx3, dx2 and dx1. And the strain energy that we have to write eventually in order for minimization or determining the stationary points of the functional is basically integral from 0 to L, integral over the cross section of the energy per unit length or energy per unit volume of the material involved in the beam times 1 minus x2 by r, and then the corresponding elemental lengths. Okay, now this is the way we are writing the strain. This is something we already introduced in the previous class. So this is the order in which we are putting them. Instead of writing it as a 3 by 3 matrix, we are taking only the 6 independent components and putting it in the form of a column matrix. And we are ordering it in such a way that the first 3 terms involve subscript 1, the others 3, the last 3 do not involve a subscript 1. So they are basically dependent on the in-plane warping alone. So that's how we basically put this. Then now we want to introduce the constitutive law over here, and in particular we are talking about an isotropic material. But even before that, in a general case, 3D stiffness, suppose we denote it by floral D like this, and that is of course given in terms of the flexibility matrix or the compliance matrix F, floral F inverse, right? And D is something which is very useful in mathematical modeling, but it is F which is actually determined in experiments, because in experiments it's much easier to apply uniaxial stresses rather than uniaxial strains. Okay, so that is the reason why in most experiments you apply stress in one direction, determine the strains in all the other directions, including of course the shear strains, and you populate the F matrix. Once you populate the F matrix using that numerical procedure, experimental and numerical procedure, you have to invert that matrix to get your D, and it's more convenient to utilize the D for most of the mathematical modeling, right? So in the case of homogeneous isotropic beam, just 2 quantities can determine this entire D. It could be one of the 2 of these 3 quantities, namely the Young's modulus E, shear modulus G, and or Poisson's ratio nu. Right. So in terms of them, the flexibility matrix, it's quite easy to see the diagonal terms, which are of course in the first, 4th and 6th terms over here. So corresponding to that, you would have just 1 by E. That's how you determine the Young's modulus of a material. And then of course the terms corresponding to the 2nd, 3rd and 5th. The 2nd, 3rd and 5th are all shear strains, and corresponding to them you have the shear modulus obtained as its reciprocal, right? And then of course the coupling between these quantities, so you have 1, 4 and 6, so 1, 4, 4, 6 and 6, 1. So basically those 3 would be Poisson effects, so coupling between the normal quantities. So that's all of them are going to be given by minus nu by E. Special case where Poisson's ratio is 0, you don't have Poisson's effect or coupling between the normal strains and the normal stresses. Right. Now we go to the 3D stiffness, and that is, whereas it is easier to write the flexibility matrix in terms of E and nu, it is more easy to write the stiffness in terms of the Lamé parameters. The expressions look more compact, that's all. And the two Lamé parameters are lambda and g. Lambda, of course, is defined in terms of E and nu. G is also can be defined in terms of E and nu as E by 2 into 1 plus nu, as you are familiar with. So once again, you have the normal stiffnesses basically given by lambda plus 2g. The shear stiffnesses are just given by big G, because there was no coupling between these, either between themselves or with the normal strain, so it just becomes a reciprocal of this. That's what you have here. And then of course the coupling between the normal strains is what results in this lambda, right? And lambda in turn is related to the Poisson's ratio and the Young's modulus, like this. And in this, of course, you can write E by 1 plus nu as basically 2g. So you can see that it is directly related to 2g as well. So 2g into nu divided by 1 minus 2 nu. So you can see different limits in this. Poisson's ratio can vary from minus 1 to plus half. That is the range that it can have for all materials that we know of. So which can be proved, of course, again mathematically using the theory of elasticity equations. Now you can see that expression, for example, if you have lambda and g, there are limits that we can talk about here, because in what we are going to do, we typically assume the g and lambda are of the same order of magnitude. Okay, in other words, all terms in the stiffness matrix are of the same order of magnitude, leave alone the zero terms, of course. The rest of the terms which are not listed here, of course, are zeros. That's known because we're talking about isotropic beam. Many of the couplings are absent. But amongst the terms which are present, all of the terms are of the same order of magnitude is an assumption that we typically use. It seems to be reasonably good if nu is of the order of 0.3, etc., which is 0.2, 0.3, which is what is observed for most structural materials that we use. But you should remember that if you're taking about all kinds of materials, you have to look at this entire range minus 1 to plus half, and in such situations you can have issues. For example, if you have a somewhat incompressible material like rubber, your nu can approach almost 0.5, let's say 0.49 or so. So then you will have in the denominator over here a very, very small number. This of course is nothing but 2g. So therefore, if you compare g and lambda, you could see that lambda is much, much larger than g in such a situation. Similarly, you could have a situation where nu is close to 0, because that is an acceptable value mathematically speaking. There are materials which have Poisson's ratio close to 0. So in such a situation, you can say lambda is very small compared to g. Okay, so you could have such situations as well. That is something to be remembered. But as I said, most engineering materials, because the range is 0.2 to 0.3, this is a reasonable assumption that we will make. This is only a simplicity in terms of the pedagogic derivation, but depending upon the specific types of materials that we are talking about, different theories can be derived using the variation asymptotic method, appropriately accounting for the difference in orders of magnitude between lambda and g. Let's continue with this simpler example. So linearly elastic material, the U3D, the energy per unit volume of the material making up the beam, is given by 1/2 gamma transpose d gamma. So in other words, it's quadratic in the gammas over here, and the corresponding stress corresponding to this, Jarmon by Cauchy strain tensor that you have here, is this particular thing. Again, the ordering is same as what you have there in terms of the components. And then, of course, it's a linearly elastic material, so it's proportional to gamma. And the constant of proportionality is this matrix D, which is a stiffness matrix. So next, we want to employ the variation asymptotic method to perform the dimensional reduction, going from this energy per unit volume to an energy per unit length, what we call as U1D. So we define, of course, variation asymptotic method. The variational part means that we need a functional, which we want to, whose stationary points we want to determine, and the fact that it is asymptotic means that we need to identify what are the small parameters, most of which we already know from the geometry and the material properties. So the strain energy per unit length, U1D, would just be given by an integration over the cross section of U3D times square root of G. So we discussed this already. So that into dx2 dx3, and we already introduced this notation of an angular bracket to indicate an integration over the cross section. If we have these double angular brackets, it means that it is an integration over the cross section, but along with square root of g present in the integrand. Okay, so the difference between a double angular bracket and a single angular bracket that you have to remember. In, of course, a situation where you have an initially straight beam, they don't make any difference, they are equivalent to each other. So your root g, of course, in this specific example is 1 minus x2 by r. So then you have the energy per unit length of the beam would just be given by an integration of that. We already have an expression for u3d from this. We have an expression for gamma over here and the elements of d over here. So it's easy to see there are three kinds of terms. Basically those which are normal strains. So those will have a coefficient lambda plus 2g and they would involve the squares of the corresponding quantities, which are the normal strains, gamma 1 squared, gamma 2 squared, gamma 3 squared. Then we have the three shear strains. Their squares would all be added up and they all have the same coefficient, which is basically coming from g, but because we have removed the factor 2 here, 2 gamma 1 2, 2 gamma 1 3 and 2 gamma 2 3 along with the square, so 2 squared is basically, that's where the 4 is coming from. Next we have the last term, which is basically the interaction terms between the normal strains, and the normal strain combinations are 1 1 2 2 and 1 1 3 3 and 2 2 3 3, and for all of them it's the same coefficient that you have there, which comes out as lambda over there. So we have this. Of course, we need to now substitute for the expressions that we have for the gammas, which we have already derived. So again, this is the overall u1d. Then we'll talk about a u1d naught, which is the leading terms of that, the zeroth order approximation, where we'll take the terms which we did not underline in one of the previous slides. So that will give us the leading terms, and then we have to minimize that, or in other words, determine its stationary points with respect to the warping, right? Okay, so now this is just repeating the expression from the previous slide. So let's say for most engineering materials, lambda and g are of the same order of magnitude. So the leading order terms of 2u1d are formed by the leading terms of gamma ij directly. So this is another simplification that we can use in the classroom purpose. In reality, you have to expand out the strain energy completely and then collect its leading order terms, and then the next higher order terms, etc., because that is the determining factor. The functional or the integrand in the functional is basically the determining factor. But here, because the matrix D that we have, let's say, are of all of the same order of magnitude, because lambda and g are of the same order of magnitude, therefore we this segregation of leading order terms and higher order terms can be equivalently made at the strain level itself instead of doing it at the strain energy level. But that is something which is not always possible. The stricter sense, it has to always be done at the energy level, just so that because we have a simplified case because of this feature, therefore we are able to do the segregation at the strain level itself, and which we already did. That's where we did, we had certain terms not underlined, certain terms underlined, and then the so-called HOT or higher order terms, right? So we have already done that. So consider only terms of order epsilon hat in gamma ij, because those are the leading terms. The next terms were of the order epsilon hat times a by r, where a is small compared to r, right? So this is what we need to retain. In other words, the terms which we did not underline. Okay. So, and of course in root g, which has 1 minus x2 by r, because we are taking only terms which are of the order of epsilon hat, this will make it epsilon hat into a by r, which is a higher order term, so that which are similar to the terms which we underlined, and therefore this root g terms will also contribute only from this part as far as the leading terms are concerned. When we go to the first order approximation, of course this will contribute as well. Which means that because root g is going to just reduce to 1, whether you put a double angular bracket or a single angular bracket, at this level of approximation is one and the same. Okay, so but in the next level of approximation it does make a difference, and this is the right thing, not this. So then we have gamma 1 1. So taking only the terms which were not underlined, we have only two terms, gamma 1 1 bar and x minus x2 kappa 3 bar. And then next higher order terms are the order of this, which is epsilon hat times a by r. Okay, this is the next higher order terms. This is not the terms which we wrote as HOT there. Those were epsilon hat times a squared by r squared, the next higher order terms. We are dropping off even those terms which we underlined. Those terms which we underlined were of this order, right? Next, we have these terms 2 gamma 1 2 and gamma 2 2. As far as the gamma alpha beta terms are concerned, they are all as they are, the exact expressions, because they are very simple expressions and they all have terms which are of the order of epsilon hat, so they remain. It's only in the gamma 1i terms, that is those three terms, that you will see this difference. And so here only w1 comma 2 is there, the rest are higher order terms. And similarly here only w1 comma 3 is there, the rest are higher order terms. Here we are not even adding plus order of something, because this is the exact expression already. We don't have any more terms in these three strain measure examples. Right. Next, U1D naught is what we have to find. The standard procedure of the variational asymptotic method has to be invoked now. So from 2U1D, which is the exact expression, we get an approximate value for the functional, which we call as 2U1D naught, which are the dominant terms of 2U1D.
So
now, yes.
Before starting there, so in the energy level we are making that assumption, right? That higher order term droppings and other things, right, sir?
That's correct.
So what we will do is just multiply them and integrate them, right? After that we will decide.
No, not we cannot integrate it because we don't know how they are functions of x2 and x3. So we cannot perform the integration. We are only talking about terms within the integrand. So we can do that multiplication of half gamma transpose times d times gamma, right? So that 6 by 6 matrix multiplies those six element strain vectors on both the sides, and then basically you have that many terms expanded out. Basically in general 36 elements, of course not all are independent because of the symmetry of D which is basically involved. So you have 21 terms in general, for example. So then you have to basically sort out there which are the leading terms. Exactly. Right. So that is essential if the matrix D had terms which were of different orders of magnitude. So in such a situation you would have to do that. But here, because lambda and G are of the same order of magnitude, therefore all the non-zero terms within the D matrix are of the same order of magnitude. So instead of expanding out and doing it, we are doing it at the strain level itself, which is equivalent. Right. So this is of course the material constants are all, let's say, of the order of E. That is, order of magnitude of lambda is E, order of magnitude of G is E. Everything is in terms of lambda and G, the lambda parameters now. And then there is one material parameter which comes, and two contributions from the strains, which are basically both of the order of epsilon hat. So the contribution of all the leading terms of U1D would be E times epsilon hat squared. Okay. So that's basically at the 3D level. Of course, when you integrate it, there will also be the area which is coming into picture, because remember this is U1D. So strictly speaking, this should be E times A times epsilon hat squared, or what we call as small a squared. Okay. So that should be there as well, because you're talking of U1D. If you're talking about U3D, then this would be correct. Next we go to U1D naught. So these are the terms which exist. So already we have written the leading terms here. So of course we are going to leave this out. So only these terms and these terms are going to be involved. So it's the same expression that we had over here. We are just going to substitute for each one of these strain components from these 6 expressions that we have. Putting that in, we expand that out. This is what we get. Right? To obtain the first approximation to warping, we have to obviously minimize this particular quantity, subject to the constraints that we have introduced. There are 4 constraints, 3 related to the translation, 1 related to the rotation. So one way of doing it is to introduce Lagrange multipliers, adding to each one of these. So there should be 4 Lagrange multipliers, 3 corresponding to this, and the 4th one corresponding to this, that we will add to the integrand of the functional, and then basically minimize that with respect to not only the w's but those Lagrange multipliers as well. So this is what it means. So you have the first variation set equal to 0 of a particular quantity, which is not only U1D naught but also lambda 1, lambda 2, lambda 3, multiplying the integrals of w1, w2, w3, and then lambda 4 multiplying the integral of this. And these, remember, are actually just angular brackets. They are not the double angular brackets, even in a situation when you go to the higher orders of approximation or when you had those additional terms contributing. So because those are just integrations over the cross section that you have over here. That should be remembered as well. Next, we can expand that out. So basically, you have the partial derivative, because remember that u1 d naught is an integral over the cross section of those of u3d, of course with the root g also involved, and therefore you would have the partial derivatives of u3d, because the unknown quantities are the warping, and they all appear as derivatives. They don't, anywhere you see in the leading order terms, you don't see w1, w2, w3 appearing by themselves. They all appear either as a derivative with respect to 2 or the 3 direction, not even with respect to the 1 direction. There was a term here which was w1 prime, which dropped out because it was a higher order term, because w1 was of the order of epsilon hat times a, and prime made it epsilon hat a divided by L, and therefore it dropped out, right? So all derivatives of w are with respect to x2 and x3. So you see that, so x2 and x3 we are representing by alpha, 2 and 3 directions. So it's a partial derivative of u3d naught, which is the integrand of this term alone, and with respect to wi comma alpha into the variation of wi comma alpha, right? We'll keep this term aside because here we need integration by parts to remove this derivative in the variation term to be taken to this. So we'll see how that can be done in the next slide. As far as the other terms here are concerned, so here you have this. So again, both these are unknown quantities, so you have to use the product rule. First the variation of this into this, and then this into the variation of this. So that's basically what you have here. Of course the arrows are removed because only the integrand is being considered here. So lambda j times the variation of wj, wj times the variation of lambda j, that is basically coming from these terms. And then from this term you have lambda 4 times x2 times variation of w3, x3 times variation of w2. So you see that through the constraints, actually w1, w2, w3 are coming in directly instead of in the form of their derivatives. Whereas through the energy, they are entirely coming in terms of derivatives with respect to the cross-sectional coordinates. Okay. So then you have this, and then of course the variation of the last Lagrange multiplier as well, multiplied by the integrand of the constraint. Okay, now let's, in order to tackle the first term there, where you had a derivative in the variation term, we have to recap something related to the integration by parts and extend it from a single dimension to a 2-dimension problem. Most of you will be familiar with that, just that you may not use it on a regular basis, so this recorrection would help in how we proceed further. So first of all, if it's in a single dimension, let's say u dv, an integral is given by uv minus integral v du. This you are familiar with the appropriate limits, of course, on all the 3 terms which are involved. Okay. So instead of v, if we had, let's say, a variation v comma x, that's basically over here. So then what we can do is, here it's a derivative with respect to x and there is an integration with respect to x. So you can think of this as just d delta v. Okay. So that's basically these 2 terms combined into d delta v over here. So now we can think of this as an integral of u times dv, but instead of v you just have delta v. So we can use the same expression in order to determine that. So you see that this is u times v, instead of v you have delta v, and again v du becomes delta v du over here, okay, with of course the appropriate limits. So now that can be expanded out. So this both at the point B, so ub and delta vb minus ua delta va. Similarly, this integration also, here you can bring back, just like how you took this derivative with respect to x out, you can reintroduce that with respect to x. Instead of delta v du, you can make it du by dx into dx, and so that's basically u comma x that you have over here times dx. So this is something which is very familiar from the single dimension, that we want to extend it to 2 dimension, because the integration that we have now is not along over a single dimension but over a cross section, which is a 2-dimensional area, right? So this is basically what we have, a domain omega, which is the cross sectional domain, it could be any shape. As of now, we are focusing on class R beams where there is no difference in order of magnitude in the two directions. That's basically taken into account. You would have a closed contour, which is the boundary of that particular cross section. Even when you had, for example, class T beams here, an I section, you would still have a single contour that you're basically going through. Of course, when you have let's say a hollow circular tube, then you would have two boundaries. There are ways of taking that into account as well. Let's not bring in those complications right now. They are mathematical things that are quite standard and handled already. Anyway, if you have a cross section like this, you have this contour gamma, which is basically taking care of that. You have introduced x1 along the aerial centroid loci, that's already there. So x2 and x3 are basically along these directions, and correspondingly you have v2 and v3. And we also introduce the concept of a unit normal vector, which is perpendicular to this entire contour, closed contour that you have. That is basically your n, right? So now let's have a similar kind of a situation. Now the integration is over omega with respect to dx2 and dx3. So it's a double integration there. So instead of what we had there, the only difference is the integrand is the same. It's just the integration is over two domains. So we have the same quantity that we had over there, u delta v, comma. It could be either x2 direction or x3 direction. One of those derivatives are there, right? So I just put it in general as delta v comma alpha, right? So now that is broken up into an integration over the contour, the closed contour, and in the direction of course shown over here for gamma. And then you have the integration over the cross section itself. And now you see that this derivative has been shifted from the variation term to the function term. So in other words, you have a u comma alpha instead of a delta v comma alpha. So that is basically what is done over here. Because eventually what we'll be doing is to get the so-called Euler-Lagrange equations or the governing differential equations for the system, we have to collect the coefficients of the variation of each of these variables, and so we cannot have the derivative of variation over here. So that's why we want the only reason we are using integration by parts here is to remove that derivative over the variation term and put it over the term which is a function. So that's basically what has happened over here, and using this we typically get boundary conditions, so that also we will see when we get there. So for example, if you had a rectangular cross section of, let's say, breadth v and height h, both of the same order of magnitude, and then the normal vector in such a situation is quite easy to see. On the surface, let's say x2 is equal to plus or minus b by 2, you see that it is along the b3 direction correspondingly for both these directions, where x2 is equal to plus b by 2, you can see it is along the plus b by 2 direction is the normal. And of course this b is the breadth, the value of the breadth of the cross section. And similarly it is for these two surfaces, the top and bottom surfaces, which is x3 is equal to plus minus h by 2. The corresponding unit vectors are along either positive b3 or negative b3. Similarly, not only do you need n, but you also need d gamma, which is basically the elemental length over here, because you are going to integrate with respect to d gamma over here. So for a rectangular cross section, there would be either dx2 on these two surfaces or dx3 on these surfaces. But because of the direction in which we are doing the integration, they would have signs as well. So when you are going on this direction, for example, because you are going in this direction, when you are going down, it would be minus dx2, whereas minus dx3, and here it will be plus dx3. Of course, we are talking about a rectangular cross section over here. What is shown is not. Right? So correspondingly, you would have for plus minus b by 2, you would have minus plus dx3, and here for plus minus h by 2, you would have just plus minus dx2. So those are the d gamma values. Once you put that there, and let's take an example where alpha can of course take 2 or 3 values. So you can take it as x2. So basically derivatives with respect to x2 for the variational term. So then you see that this is what that basically boils down to. Once we substitute for those terms, then you can see that this is what the integration would basically involve. So it is not there on all the 4 edges, it just boils down to just 2 edges for which it is non-zero contributions that are there, and this is the boundary term as far as the boundary term is concerned. So then, of course, when you have an expression like this, you can see that this is something which is valid on the boundary, and so you typically will have combinations, either a natural boundary condition or a geometric boundary condition. That's what happens in this case as well. So suppose V is not specified on the boundaries, then obviously this quantity has to go to 0. On the other hand, if V is specified, then you cannot say anything about this. It's just that the delta V would be equal to 0. So now let's go ahead and solve this problem that we have on hand. What was there was a general introduction to integration by parts, which we have to apply for the specific problem on hand. So here we have the notation for this quantity integration of 1 over the cross section, which we call as the A. We'll now hereafter call it as just A. And then I alpha would be the moments of inertia about the two axes x2 and x3, the cross-sectional axis, the coordinates that we have. So I2 would be integration of x3 squared, whereas I3 would be integration of x2 squared, both over the cross-sectional area. Now again, see, in these cases root g is not involved because x2 and x3 are not curvilinear coordinates. It's only x1 which is a curvilinear coordinate, and therefore that root g comes in only in a volume integral, not in the cross-sectional area integral. So that's another thing to be remembered. So the following functions uniquely satisfy all constraints and minimize the approximate energy. So you can verify this. All that you have to do is to set delta u1 d not equal to 0 the way we did, along with the Lagrange multipliers, etc. And then you can see that this turns out to be the solution. As far as the out-of-plane warping is concerned, it is equal to 0 for this simple example that we have taken, an isotropic beam with initial curvature in only one direction, constant all through, and planar deformation. In such a situation, you can prove that the warping out of plane is equal to 0, whereas you do have warpings which are in the plane, and these are obviously dictated by the Poisson's effect. For example, if nu were equal to 0, the Poisson's ratio were equal to 0, both these terms would vanish and W2 naught would be equal to 0 as well. So there will be no Poisson effect. And this is quite easy to see. This basically coming from the extension. So the extension will have, if you take the derivative with respect to the 2 direction, you will have a W2 comma 2, which is nothing but a gamma 2 kind of a stretch, which is basically happening because of a gamma 1 that you have. So that is basically, you can see that contribution for that. It's proportional to the Poisson's ratio, proportional to the extensional strain that you're having, and the x2 term ensures that the W2 comma 2 has a contribution. Similarly, you can see how the kappa 3 bar contributes as well, because kappa 3 bar contributes bending, which will involve both extension and compression in different parts of the cross section. Where there is extension, when you have a positive Poisson's ratio, in the other direction you will have compression, and vice versa. And that's why you see terms involving x2 squared, x3 squared, etc. over here. Similarly, you have W3 term over here as well. Once again, there is a quadratic contribution because of kappa 3 and a linear contribution of x3 in terms of the gamma 1 bar term. Then minimized value of u1 d naught turns out to be a very familiar first approximation to u1 d. We've been stressing this fact. Even though Timoshenko theory is not asymptotically correct, Euler-Bernoulli beam theory is indeed asymptotically correct at its level. Not to say that Timoshenko theory is worse than Euler-Bernoulli theory, just that it's a refined theory compared to Euler-Bernoulli beam theory, but it has not been refined in an appropriate manner, and that's the reason why you need so-called correction factors like the shear correction factor. Keeping that aside, as far as u1 d naught is concerned, it is very similar to the so-called Euler-Bernoulli beam theory, but generalized a little bit because we are including not only bending but also extension into this problem, and initial curvature is involved as well. So familiar first approximation to the one-dimensional strain energy density, that is the energy per unit length of the beam for planar deformations alone, is basically this. There are just two terms. Of course, we are restricted into isotropic materials, so therefore a lot of couplings have dropped out as well. Nonetheless, you have EA, the axial stiffness, very familiar, and gamma 1 bar squared, the extensional strain squared, again kappa 3 bar squared, the curvature squared, multiplied with EI3, which is a very familiar notation for the bending stiffness in the appropriate direction. So this is all that we get. But you see that you are still allowing for in-plane warping of the cross section. In fact, you did allow for out of plane warping also. It didn't have a leading order contribution. It will have a contribution in the first order approximation, but in most theories, when for example Euler-Bernoulli derived their theory, or it's derived in textbooks, a lot of additional assumptions are made in order to derive this. One of them would be that the cross-sectional plane is rigid. We didn't make that assumption. We still ended up with the same result, fine. But it is not necessary to make some of those assumptions. As we have been saying right from the beginning, you have to make an assumption only if it is both necessary and required in order for some simplification to happen. Okay, and it's also applicable for the particular problem. So here it's not even applicable, because we see that under the same theory, indeed the cross section is not rigid. It does undergo deformation within its own plane, even as far as the leading order approximation itself is concerned. So the recap is that no ad hoc assumptions were made, such as cross-section rigid in its own plane, or some textbooks even say nu equal to 0, which is equivalent of saying this, because that's what, as we saw here, if you set nu equal to 0, you would get W2 and W3 equal to 0. So without saying so, that is kind of inherently assumed in some derivations, and that's how they end up getting that result. So such assumptions neither necessary nor correct in any sense, including asymptotically. So that's one of the issues. Next is, so that's basically what we are saying. It's neither necessary nor correct. Okay, so only if it is both, then we should utilize such an assumption. So to find the next approximation, which is what will introduce certain interesting terms which we can discuss, all that we have to do is follow the variation asymptotic method, just like the general procedure that we introduced in the previous class. All that we do is perturb the warping. We already got a particular solution to the warping. This is a leading order solution. The actual W is a little more than this, a little more refined than this, may contain higher order terms. So what we do is, to that Wi naught, that is I is equal to 1, 2, 3, this is the 0th order approximation, we add a perturbation term Vi, so that your warping now Wi is given by the sum of those two, whatever solution we have already got, and perturbation which we want to determine in terms of Wi naught. Okay, so now we also should recollect that your Wi naught is of the order of epsilon hat times A, which is what we concluded, especially looking at the terms gamma 2 2, gamma 2 3, gamma 3 3. So from that, so at the most your Vi can be one order higher than this. Okay, it cannot be bigger than that. It cannot be larger quantity than that. And this amongst the small parameters, we have two small parameters. One is epsilon hat, which is very small. It's order of 10 power minus 2. The other one is A by R, which is of the order of 10 power minus 1. So let's say the perturbation is at the most 10 power minus 1 times this. So that's why we multiply this by A by R. So it becomes A squared by R multiplied by epsilon hat. So that is the estimated order of magnitude of V hat. V. Of course, it can turn out that when you find the solution, it is even smaller than this. It is possible, but it cannot be bigger than this because of the fact that we have already extracted everything which is of this order of magnitude, and there is no intermediate small parameter between these two. Okay, so that is the logic involved over there. So with this, we go into the first order formulation. So this is expanding out what we mentioned in the previous slide. So basically you have the three direction warpings are the corresponding W naughts plus V1, V2 and V3. Okay, so these are the additional terms. That was, of course, the solution was 0. So V1 is all that is there to W1, whereas these are already had solutions, and therefore you have an additional perturbation of V2 and V3. So now we substitute this new warping, which involves up to epsilon hat into A squared by R terms, that we substitute into the strain expressions, because we want to go into the energy. To go into the energy first, we need to get the strains. So strain expressions, and this time we go for the next higher order terms as well in the strain, so that we get the next higher order terms in the strain energy, right? So earlier we took only the non-underlined terms. Now we bring in the underlined terms as well in the original expressions that we had. And of course there are even more higher order terms which we still continue to write HOT or higher order terms, right? So that's the case with those three. These of course are exact expressions for the in-plane strains within the cross section. Now we go ahead and go to the original integrand, which is U3D, which is once again quadratic in the gammas, with these gammas as the expressions for it. And we retain now all terms which are one order of magnitude higher than what we already had. Remember, we had terms which were the material order of magnitude E times epsilon hat squared, because epsilon hat was the order of magnitude of the strains. Now we go for one level higher, and one level higher means A by R or A by L equivalently, right, with respect to the leading terms. So the next approximation of U1D, we will denote it as U1D subscript 1 to distinguish it from U1D naught, which was the 0th order approximation. So this will include terms which are of the order A by R with respect to its leading terms, and those leading terms of course gave the classical theory that we already got in terms of extension and bending. So now we go into the first order beam energy and the constitutive law. So here we have Vi is of the order of epsilon at A squared by R. Already we said that because the Wi naught were of the order epsilon at times A. So that multiplied by A by R is what Vi is. And we find that the solution, if you do find the solution, is the same as what was estimated. That is indeed that order of magnitude as indicated in this. So Vi contributes terms of the order Ea times epsilon hat squared. That alone was the 0th order approximation. Now, because in the strain you are taking one term A by R, and you know that the strain energy is quadratic in the strains, so therefore it becomes the square of that, okay, because you are having a perturbation A by R in the strains, in the displacements, and therefore the strains. Therefore you, in the energy, because it's quadratic, you would have A by R squared as the correction to that, so to U1D. Now, but if you look at the difference between U1D1 and U1D naught, U1D naught had all the terms epsilon hat squared times E, right? Now, of course, multiplied by the area. But now, the additional term should have just one order of magnitude higher and not two orders of magnitude higher, right? So, in other words, only up to A by R should be what is actually required in order to go in steps, okay? Otherwise you'll be jumping. Already you had up to epsilon hat squared, you would directly jump to A by R squared. So you'll be jumping one level higher. So you don't need to do that. You can refine it in much smaller steps because you have this small parameter. So what you really need in as additional terms at this level is only the A by R corrections, right? As far as the energy is concerned, right? Now that is basically larger compared to what would be contributed by your VIs. Even the leading terms contributed by Vi would be this, which is much smaller than what you have over here, right? So in other words, Vi is not even essential to determine your U1D1, okay? Of course, you have a methodology in terms of how to determine Vi, how to substitute that, get U1D1, but if your interest is to get only the next order of magnitude terms in the energy, they are only A by R times the classical measures, whereas Vi contributes A by R squared times the classical measures. So you don't need the Vi to be determined. In other words, you might get the governing differential equations for Vi, but you don't need to solve them in order to get the energy of the next higher order approximation. So unnecessary to find Vi to find U1D1. So this is basically your U1D1. This is what it turns out to be. Of course, this is your U1D naught, which is the original. Now these underlying terms are basically the additional terms, all of the order A by R compared to those two terms that you have there, and this is what is there. Of course, you still have an integration over there, and this is in terms of W2 naught, which was already determined. So in other words, you see that Vi is not appearing in these terms. It would appear in these terms, okay? So it would appear in these terms. That's what this is basically saying, okay? So you don't need to solve for Vi. The W naught itself is sufficient in order to determine all of these terms and go to the next higher order approximation in the energy. So let's focus on these additional terms, because this we have already got, and this is something which has to be bothered about in the next order of approximation, if at all it is essential. So let's focus on this new term that we have got and see if we can simplify that further. Okay, so we take that. So basically all that you do over here is to rearrange terms and to simplify them. This is basically two quantities squared, so you can use a minus b whole squared is equal to a squared plus b squared minus 2ab to expand that out, multiply with x2, and you know where this integration has to be applied is only on functions of x2 and x3. Quantities which are not functions of x2 and x3, which are functions of which are 1D variables, will be taken out of those angular brackets. So that is basically what is done. Some terms will go to 0 as well, and because of the fact that we have chosen the centroidal area centroidal axis as the loci of area centroidal axis as the reference curve, etc. Because of some of those reasons, some of the terms will vanish, and basically this is what you will end up with. Now we go back, because this is in terms of the one of the zeroth order warping components, and that we have already solved for in the previous approximation. So we take that expression and we can substitute that here to further simplify this. So when we do that, this additional term, I am not writing these two terms which are already there and the higher order terms, only the new term that I am writing over here. So this is what it boils down to after substitution of W2 naught. Now based on this additional term that you have in U1D1, the corresponding 1D constitutive law can be obtained. 1D constitutive law is a law which relates the generalized forces and moments of the 1D, that is basically the section forces and section moments, F1, F2, F3, M1, M2, M3, all functions of X1 to gamma 11 bar, kappa 1 bar, kappa 2 bar and kappa 3 bar. Okay. So in of course when you bring in the transverse shear strains, you will have 2 gamma 1 2 and 2 gamma 1 3 there as well. Here we don't have that. In fact, we can leave out even F2 and F3. You only have to talk about F1 and the 3 M's, right? So based on U1D1, the corresponding 1D constitutive law can be derived by taking the derivative of the energy with respect to the energy per unit length with respect to each one of the strain measures. So for example, if you want to get the axial force resultant, you have to take the derivative of energy per unit length with respect to the strain, the 1D strain undergone by the reference curve, right? So that's basically your gamma 11 bar. So when you take that derivative, you end up with F1. That relationship between F1 and gamma 11 bar would constitute one of the constitutive relationships. Similarly, when you take the derivative of the energy with respect to kappa 3 bar, the other strain measures that it depends upon, you will get the M3, the bending moment about the third direction. So if we actually substitute for that U1D, of course taking into account these two terms as well, and take that derivative, then you see that F1 is given by this. The first term is eerily familiar. Your axial force resultant is given by the axial stiffness times the axial strain that you are already familiar with, and that's what you got in the zeroth order approximation. Now what happens is in the first order approximation, you get an additional term which is contributed by the bending as well. In other words, bending contributes to the section force, and that is because you had an initial curvature. If you didn't have an initial curvature, your R would have been infinity and this term would not have existed. So that initial curvature is making the bending curvature to contribute to the axial force resultant. So and you will have a similar corresponding relationship when you go for M3 in terms of gamma 11 bar as well, because this is a coupling term which will be present in both. So now let's talk about the bending moment, and that, of course again here you have the higher order terms which can if necessary be determined by going to higher orders of approximation using exactly same procedure that we followed for the first order approximation. So when you want to determine the bending moment M3, which is again an internal stress resultant, so that will be a partial derivative of energy per unit length of the beam, approximation at the first level, with respect to the bending curvature kappa 3 bar. So that all that you have to do is to take derivative. So this term would contribute. Similarly, this term and this term would contribute as well when you take the derivative with respect to kappa 3 bar. And this is basically what it boils down to. So again, this is what we already had. So bending stiffness times the curvature is the bending moment. Again, very familiar. In addition, of course, this term, the axial strain contributing to the bending moment. So in other words, what has happened is that the neutral axis and the centroid, area centroid are no longer coinciding. That's the reason why you see that there is an extension bending coupling which is happening, and that in turn is because of the presence of the initial radius of curvature. So if the initial radius of curvature were infinite, or there was no initial curvature, that basically means that in such a situation you would not have this additional term. That is one term, which is the coupling term, but you also see there is another term which is contributing to the bending stiffness itself. So in other words, EI3 alone is not the bending stiffness. There is an additional bending stiffness term which is contributed by this, because this is linear in kappa 3 bar. Okay, just like this term is linear in kappa 3 bar, so that is the bending stiffness, 0th order. There is a correction to that bending stiffness that also depends on the initial curvature. So the initial curvature can make the rod either more difficult or more easier to bend depending upon what this turns out to be, the sign of this. Okay, so let's just summarize that in a matrix form, whatever result we got in the previous slide, the two derivatives that we took of the energy per unit length of the beam with respect to gamma 11 bar first and with respect to kappa 3 bar. Those are the two equations. We are clubbing them together in this matrix equation. So there you see that this is the so-called 1D stiffness for this example. It's a very simplified example because we didn't consider, of course, transverse shear strain, therefore F2 and F3 are not appearing here. We consider only planar deformation, so M1 and M2 are out of this problem. So only F1 and M3 are there. But even in this, there are lots of insights that we can get. First of all, into how we apply the methodology, and again in terms of the results, the interpretation of the results. Again, the non-underlying terms are what you would have in the classical theory. So only you would have a diagonal matrix consisting of EA and EI3. The off-diagonal terms, in other words, would be 0. No coupling between extension and bending. Because of the presence of this R, you have this coupling, and of course you see once again symmetry is basically there. And then, as we said, in the bending stiffness, not only EI3 but also due to R, there is a finite R, there is a contribution in further stiffening of the in bending of the cross section. Then of course it is also possible to determine from the orders of magnitude that we have what would be the next higher order of magnitude if it would appear, because we already have the orders of magnitude of each of the strain measures, the additional terms, and therefore of the energy, and therefore its derivative with respect to the 1D strains, and from that we can estimate what would be the next higher order terms if it were to be determined in terms of epsilon hats and the A by R or A by L. So the underlying terms are of order A by R with respect to the leading terms. In other words, they are smaller compared to whatever is already there, that is compared to these. Then and they represent, what do they physically represent? A slight change in bending stiffness. That's what this term represents, due to the finite R that you have over here. And of course, even if you had initial curvature, but if it were a doubly symmetric cross section, this term would go to 0, and therefore you would see that even with initial curvature, there would be no change in the bending stiffness. It would remain EI3 if it were a doubly symmetric cross section. Okay. Of course, for this problem, we have already assumed for planar deformation that the cross section is symmetric about this plane. So, in other words, if you look at it either in front of the screen or behind the screen, it would look similar cross section. But we didn't assume any symmetry as far as up and down is concerned, basically that geometry that we talked about. So, if you had a doubly symmetric cross section, then even the presence of a finite initial radius of curvature does not cause the bending stiffness to change, at least up to this level. It may change at this level, we don't know. Next is the stretching bending coupling. So these two terms, which means that, as I already said, a shift in the neutral axis from the area centroid, and that again is because of the presence of a non-infinite R. There is a finite value of the radius of curvature, initial radius of curvature. So let's recap that only assumptions in the dimensional reduction were the fact that epsilon hat is small compared to 1 and A by R the whole square is small compared to 1, because A by R was assumed to be of the order of 10 power minus 1. This was assumed to be of the order of 10 power minus 2. So next approximation would be U1D2. We're not going to do that, of course, but new terms approximately order A by R whole squared in U1D with respect to its leading terms. Whereas here we got terms which are A by R with respect to the leading terms, right? So we'll go to the next level. If we do, then it would be A by R squared with respect to the original terms, the classical terms. So with respect to its leading terms, so then associated what those terms, new terms, additional terms in the energy would be associated with large initial curvature and transverse shear effects. Okay. So in other words, if your R was not very large, that is, this R was not very large, it was reasonably small. We talked about one where it is of the order of L. In another situation, we talked about it bending around itself, where it would be of the order of A, let us say. So situations like that would come out to the open, what kind of contributions that would have. Then of course the transverse shear effects would manifest themselves, because they are of that order of magnitude. And then to find them requires solving the Euler-Lagrange equations governing VI. Remember, this VI we already talked about are the first order warping perturbations. We didn't determine them. Without determining that, we got the constitutive law, and before that the energy as well. Okay. But if you want to get this, you don't need to get the second order perturbation. You don't need to solve that. You just need to solve for the first order perturbation itself, substitute that into the energy, you will get the next order correction, and from that you will be able to determine these two corrections that we're talking about over there. And substitute the warping, which is the first order warping, which is the classical theory, whatever warping was there, which was only W2 and W3, the in-plane warping, purely Poisson's effect, and then the VI, which we didn't solve for. That together, if you substitute into the energy, into the gamma, first of all the strains and then into the energy, then you would get that. So asymptotically correct 3D strain field up to not only epsilon hat, but epsilon hat times A by R, which we didn't do at this stage, because we are only interested in the energy, what correction we are requiring, that is up to A by R. We didn't look at in the strain field. If it is A by R, then in the energy it would become A squared by R squared, the next second order approximation we will go to. So with this, I think we'll stop. In the next class we will apply the VAM to a general composite beam problem without all this planar deformation, etc. And also remember, we took isotropic example for the constitutive law. We'll do away with that. We'll take a general composite example. And once we are done with that, we will also introduce briefly the one-dimensional theory which is required to solve the reference curve problem. Okay. So I think we can have the next class on Friday.